Hello and welcome to the next video of our current transformer model. Today we want to deal with a simple model of differential protection. This is exactly what this video will be about. At the beginning, we want to clarify which circuit diagram the differential protection characteristic is based on, which currents have to be added, what the differential current and the restraint current mean. Any electrical equipment in which the currents can be added in phase is suitable. A transformer would not be appropriate in this case, as it has winding connections which must be considered. There, the currents in one phase cannot be added arithmetically, for example. We will take a power cable instead, which has a breaker and a current transformer at each end. In the worst case, one current transformer is saturated and the other isn't. This scenario results in greater imbalances, which is why it is particularly interesting for us. Let's assume that a short circuit happens here on the right side. The consequence of this short circuit will be a current flowing here. Let's name it I1. Each current transformer records the same current I1, for we have taken a power cable as an example. We further assume that the left current transformer transforms the primary current into the secondary side without an error, and that the transformation ratio Kr is equal to 1 in both current transformers. Then the secondary current of the left current transformer becomes I1, and for the right, I2. Now we need to compare these currents. In this case, the differential current, Idiff, is equal to I1 minus I2. This current minus this one. Since on the primary side the current I1 is always the same, we can conclude that the differential current can be equated to the magnetizing current of the right current transformer. That is, it corresponds to the difference between its primary and secondary currents. Instead of comparing secondary currents of two distant current transformers, we compare the currents of only one current transformer. Here, the primary winding of the right current transformer is one input of the differential protection, and its secondary winding is the other. Hence, we can state that numerically, the differential current is equal to the magnetizing current. But what problem can we encounter using the differential protection compared to the instantaneous overcurrent protection we discussed in the previous video? Unfortunately, saturation of one current transformer can lead to false tripping of the differential protection. In the event of a short circuit outside of the protected area, the transformer, the generator, the power cable, or the bus bar will be disconnected from the power system. And this is usually a nightmare scenario for the utility or grid operator, as it would mean power outages for many power supply consumers, including power factories, hospitals, and so on. Therefore, such events must be avoided at any rate. Now let's start with a simple differential protection. Its corresponding logic diagram looks as follows. So using the currents I1 and I2, we calculate the differential current and the restraint current. We have denominated the restraint current as I step for its stabilizing property. These two currents are inputs of the pickup characteristic of the differential protection. If the operating point is in the tripping range of the characteristic, a trip command will be issued for the breaker. If the operating point is in the stabilization range, it means normal operation and therefore no tripping. But what can result in false tripping of the differential protection? For example, In the case of an external fault, we can see how the restrained current becomes larger. These digits next to each operating point represent the time in milliseconds, by the way. At 0 milliseconds, the point is in the origin, meaning normal operation. The point moves along the x-axis to the right as the restrained current increases. And after saturation, as can be seen here after 30 milliseconds, for example, the operating point moves upwards because the magnetizing current gets bigger. Here is its fundamental frequency, going up slowly. I also would like to mention straight away that both the scale and the shift are activated. Therefore, you can zoom in any part of this diagram. Here it is important to note that the operating point first moves to the right, and then after the saturation has set in, it kind of shoots up. The usual pickup characteristic, with a threshold for example of 0.3 pu and a slope of 0.4, will of course trip, because the operating point is in the tripping range. The differential protection always trips without delay. That's why we would get a trip command here. Will it always be like this? Of course not. In the previous video, we have seen that the protection works correctly even if saturation time of the current transformer is much lower than the pickup time of the instantaneous overcurrent protection. However, the differential protection doesn't always pick up at fast saturation. This depends primarily on the degree of saturation and the threshold level. For example, if we change the fault inception angle, we can simply simulate a scenario where there is no large imbalance and the differential protection no longer picks up in this case. Please note that we are analyzing the movement of the operating point in the plane opened by these two currents. Hence, it's absolutely irrelevant for us how fast the current transformer is saturated and what time the protection device needs to measure the current correctly. It is obvious here that as long as the operating point is below the tripping range of the characteristic, there will be no false tripping. This is a simple fact, but one that is often forgotten. Instead, one often tends to compare times with each other. In fact, the model uses the DFT algorithm, which means that the correct value is only known after 20 milliseconds. With this setting here, however, the current transformer saturates already after 13 milliseconds, and we still have no false tripping. The operating point approaches the tripping range of the characteristic, but does not cross it. Again, a direct connection between the pickup time of the protection device and the saturation time of the current transformer does not really exist, as was the case with the instantaneous overcurrent protection. One has to consider each case individually, and in this one, tripping will not occur. But of course, this simple differential protection, according to this logic scheme, is not enough. Because as soon as we change the fault inception angle, the operating point will enter the tripping range. Well, how can we fix this and optimize our protection scheme? For example, we could add the second harmonic. The possibility of setting the second harmonic is available in virtually every differential protection, because it makes possible the detection of inrush currents, for example, in the case of an unloaded power transformer. The inrush current occurs on the transformer side that is energized, and therefore corresponds to the differential current. So if the content of the second harmonic in the differential current is high, it is a clear indication that this is the inrush current, and not a current caused by an internal fault. Now we can add the second harmonic to our logic scheme. In the model, the content of the second harmonic is color-coded. If the operating points are green, then the content of the second harmonic in the differential current is higher than 15%, whereas lower percentages of the second harmonic make them red. Here we can observe that the operating points are actually inside the tripping range, and in theory, a tripping command would be issued. But the content of the second harmonic is quite high, and therefore all the operating points are green. And if the differential protection has got an inrush current detection, then it will not pick up, and the breaker will not trip. But the application of the second harmonic can also be problematic. First of all, this function is prone to failures in case of strong saturation. If we set a high primary time constant Tp, here for instance 60 milliseconds, and adjust the fault inception angle, then we can observe that the operating points in the tripping range turn red, an indication that the content of the second harmonic is lower than 15%. In this case, the protection will pick up. Secondly, in order for us to really determine whether the second harmonic blocking is applicable, the entire course must be calculated. That is, from the fault inception until the current transformer isn't saturated anymore, to make sure that the content of the second harmonic always stays above this threshold IH second. And of course it's pointless to compare the calculation speed of the second harmonic with the saturation time. It is basically irrelevant how fast the second harmonic is calculated, since its content can decrease somewhere around 35 milliseconds, which in turn will result in a trip comment. We have thus established that this differential protection can still malfunction. However, we have not yet taken the saturation time into account in our analysis, because so far we have only been looking at the overall behavior and the movement of the operating point in the plane. And exactly for this reason, special algorithms have been implemented for the differential protection, in particular, which enable blocking in the case of current transformer saturation. These saturation detection methods can have different names. For instance, additional stabilization. But all these methods have one thing in common. In the event of an external fault or a motor startup, the restraint current rises steeply, while the differential current is close to zero during the first milliseconds. That is, just before the saturation kicks in. We can observe this behavior in the diagram. We see how the operating point first moves to the right and then shifts upwards after saturation, which occurs after 8 milliseconds in this case. And especially for the methods already mentioned, it is of great importance that within the time range, beginning with the fault inception and the moment when the saturation begins, the differential protection is capable of performing and processing the required measurements. For in this time range only, the restraint current is high and the differential current is almost zero. One could also say that there is a race between the protection device, which has to understand that the fault is happening outside of the protection zone, and the current transformer, which remains unsaturated for some milliseconds. It is therefore really important for the protection device to have some time before the current transformer gets saturated. A time which is required by the saturation detection algorithm in order to recognize the external fault. Hence, a time-limited trigger must be used, blocking the differential protection function. A subsequent entering of the operating point into the tripping range of the characteristic is therefore no longer critical. For the given example, an area could be specified here, for instance starting at 2 pu, a zone with the additional stabilization. And if the operating point first enters this zone, and immediately after that, the tripping range, the differential protection still won't trip. You could find such graphs in the equipment manuals of domestic as well as foreign manufacturers. The transition of the operating point from the stabilization zone of the characteristic into its tripping range can be determined in different ways. The restraint current and the differential current can be calculated for each instantaneous value. This way, the algorithm will be able to understand within 2 to 5 milliseconds that the fault happened outside. Also, phasors can be analyzed, like it's implemented in this model. However, this results in the application of the Fourier filter. In this case, 10 to 15 milliseconds may be required to detect an external fault. Having said all that, it makes little sense to ask the protection device manufacturer for the pickup time. In the case of the differential protection, it must first be determined whether an algorithm is implemented that goes beyond this logic and blocks tripping in the event of an external fault. If such an algorithm exists, the next question would be what time this algorithm needs to detect an external fault. And these times must then be compared with the saturation time Tsat. If such a saturation detection method doesn't exist, then no other time can be logically compared with the saturation time. The only possibility remaining is to calculate the whole course in order to find out whether the operating point will reach the tripping range or not. If it does, we still have to analyze the second harmonic content, the level of which can also be decisive for the tripping. I would also like to use the model to show one more scenario that renders the comparison between the saturation time Tsat and the pickup time even more futile. With high primary time constants, for example 90 milliseconds, and small short-circuit currents, saturation can also occur much later. In this specific scenario, we can see that in the case of an external fault, the restraint current and the differential current have already been calculated after 20 milliseconds, with restraint current being very high and the differential almost zero. It means that the differential protection has reliably measured all quantities and keeps watching the process. But after about 51 milliseconds, the saturation kicks in and the operating point enters the tripping range of the characteristic already after 55 milliseconds. It's unimportant that the currents were calculated correctly. Instead, it is crucial that the operating point reaches the tripping range after some time, resulting in false tripping. Now, if I'd summarize what this video is about in just a few seconds, it would be this. First, low saturation times do not necessarily result in false tripping. The decisive factor is where the operating point is located inside the plane with the differential and the restraint current. Second, false tripping can also occur with high saturation times, as we have just seen. Third, the saturation time must be compared with the speed of the special algorithms that are capable of detecting external faults and reliably block the differential protection when the current transformer is saturated. In the end, a few words about the options to the right of the differential protection diagram. So far we have dealt with the external fault, because it represents the worst case. With this option, we can simulate an internal fault as well. If we select it, we can see that the operating point immediately jumps into the tripping range and remains there. It is obvious that saturation does not have much influence on the whole process. The operating point enters the tripping range just as well, since the pickup value is usually set about 1 pu. Therefore, all operating points are also in that area. Likewise, different calculation methods for the restraint current can be evaluated here. The difference in the formulas is more visible in the behavior of the differential protection in case of an internal fault, rather than the external one. Furthermore, the feed-in direction can be determined for the internal fault. In the case of the two-sided in-feed, we have simply assumed that the currents I1 and I2 are equal, although this case can practically never occur, since the fault is fed by two different power systems. For the one-sided feed-in, on the other hand, no simplification was necessary. Here, the differential current equals the short circuit current at the fault location. That's it for now. I hope you've got some intuition about the differential protection part of our model. You could give it a go yourself if you're interested. You could play around with the phasor diagram and the time constants and see what happens with the saturation time and what impact it has on the differential protection. If you have any questions, please don't hesitate to ask them in the comments below. Have a nice day. See you in the next video.